What is she? Okay. I'm already. What is she?
Alrighty.
I'm already.
Good morning, everybody. And welcome back to Calc 1. My first today is I have a quiz ready for you on Standard 8. And then we're going to continue our discussion of transcendental functions and their derivatives, looking a little bit more at trig functions in the first half of class today. And in the second half, we will switch our focus to doing some review of exponential and logarithm functions. As far as office hours go, I've got my usual office hours today at 11 and at 2. Tomorrow morning, I have to cut my office hour 15 minutes short because of a faculty meeting that is going to be heavily centered around the math department that we need to talk about. And but I will have my normal afternoon office hour from 1 to 2. As far as homework goes, no new homework, but you have a homework from Monday that is still due on Friday. So, one day, some engineers are out trying to measure how high a flagpole is. The problem is, they only have a measuring tape, and they don't know how to slide the measuring tape up to get all the way up to the top of the pole. So a mathematician walks by and asks what they're doing. They explain. The mathematician says, "Oh, that's easy." He takes the pole out of the ground, lays it down flat, and then measures it. After he leaves, one of the engineers turn to each other, and one of them says, "Stupid mathematician, that's typical. We tell him we want to know the height, and he gives us the length. What gives?"
I'm really confused.
All right. Any questions or comments before I pass out the quiz? In that case, go ahead and put everything away. It is quiz time. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes in, please. Alrighty, so before we get started, I have a quick announcement. Apparently somebody left a bucket of soapy water in the front of the room. So if this is yours, make sure to pick it up on your way out. Also know that if you answer any questions incorrectly in class today, you might get dumped on. So you've been warned. Okay, so yes.
Do you have any extra standards I could make that packet?
Sorry, I didn't bring any extras with me. If you email me after class, and I'll send you one. So if you recall from last time, we kind of did some review of the basic properties of the sine and cosine functions from trig, where they're both these functions that kind of oscillate back and forth between +1 and -1. And they kind of have interesting behavior where they reach a point of interest every pi/2 units, where sine of x, starting at 0 and going to the right, has a y value of 0 to start, goes up to 1 at pi/2, down to 0 again at pi, down to -1 at 3 pi/2, etc. And cosine of x behaves very similarly, except it starts at a y value of 1, and then goes down to pi/2, pi, up to 3 pi/2, 2 pi, and so on. And towards the end of class last time, we took a look at how to find derivatives of the sine and cosine functions using some the sum rules for cosine and sine and the limit definition of the derivative. Anybody remind me, how did we differentiate sine? What did we get when we differentiated sine of x? Yeah?
Cosine of x.
Cosine of x. And how about the derivative of cosine of x?
Negative sine of x.
Negative sine of x. Good. You remember. I don't have to pull the bucket out yet. And so if you kind of look, you can even sort of see how cosine kind of corresponds to the derivative of sine, and that at points like pi/2 or 3 pi/2, where sine of x has a horizontal tangent line, cosine of x at those values is going to be equal to 0. So the points where sine of x has a slope, a tangent line slope of 0, cosine of x is going to be equal to 0. And similarly, points on the graph of cosine of x at say 0, pi, etc., where cosine of x has a horizontal tangent line, sine of x is going to be equal to 0 at 0, pi, etc. So sine and cosine have this sort of neat relationship going on, where anytime one of them has a tangent line that's horizontal, in other words, where the function has a slope of 0, the other function is equal to 0, meaning it takes on a y value of 0 at those points. So what I wanted to start by doing today is kind of take a look at a couple of the other trig functions. Specifically, take a look at tangent of x, which is defined to be equal to sine over cosine. And if we want, we can draw a quick graph of what the tangent function looks like. And it's going to look something like this. Sort of a wonkier looking function than sine or cosine. What do you all think? You said last time that you thought that sine of x and cosine of x were always continuous over the whole number line. Does tangent of x look like a function that's always continuous? No, we're scared to answer because you know the bucket's right in front of you. Rachel?
It is not continuous.
Where is it not continuous?
Pi/2 through pi/2, negative pi/2.
And it's going to turn out to be the case that this sort of pattern is going to continue, and at any odd multiple of pi over 2, the function is going to fail to be continuous. Why is it not continuous there?
Because there's a vertical asymptote.
Because there's a vertical asymptote. The function's not defined at these points, because if we were to look at, say, x equals pi over 2, if we tried to take sine of pi over 2 divided by cosine of pi over 2, we would get 1 over 0, which is undefined. So the function's not going to be defined at these odd multiples of pi over 2. And also the limit's not going to exist. From the left, it looks like it's going to positive infinity. From the right, it's going to negative infinity. So I would say not continuous at any odd multiple of pi over 2. But it is going to be continuous everywhere else. And since it is going to be continuous over most of the number line, everywhere except at these odd multiples of pi over 2, I think we can still talk about how to take its derivative. Josh, as I recall, you were eager to do this last time. How would you approach taking the derivative of tangent? Taking limit as h goes to 0 of sine of x plus h over cosine of x plus h minus sine of x over cosine of x all over h?
Could you just plug in the stuff we solved in for yesterday?
Plug in how so?
Like, for the derivative of sine, we calculated for cosine of x, and then the negative, then over negative sine x. But you have to use the quotient rule.
Ah, you want to use the quotient rule and kind of rely on the derivatives we already took?
Yeah.
Thank you. I was worried you were going to make me use the limit definition here, which would not have been fun. Yeah, sine and cosine, we kind of had to do the hard way, finding their derivatives. But once we know these derivatives, we're welcome to just kind of use these as facts. We don't have to reinvent the wheel, so to speak. So I like Josh's idea, which is if we want to differentiate sine of x divided by cosine of x, why not just use the quotient rule? Meaning the derivative of tangent of x, which is the same as the derivative of sine of x divided by cosine of x. We can do some good old-fashioned low d high, derivative of sine, which is cosine, minus high. D low, derivative of cosine is negative sine. Merely, low squared, down below. And so we end up with this cosine of x times cosine of x minus sine of x times the negative sine of x all over cosine squared. Which we clean this up a little bit, will give us cosine squared. Minus minus becomes a plus, sine squared x, all over cosine squared of x. Is there any way we can simplify this? A way that's a little bit nicer? Please?
Can you cancel the cosine squared?
Cancel this out from cancel this out and this out? I don't think we can, mainly because if we wanted to do that, we would have to factor a cosine squared out of the whole numerator. If we had something like cosine squared times sine squared over cosine squared, then I think we could do that because we have a factor of cosine squared we factored out of the whole numerator as a multiple. But with a sum like this, I don't think we can quite do that. Be nice if we could, but unfortunately not. Avery?
Can you split the fraction into two parts?
Ooh, okay. So what would that give us?
Cos squared x over cos squared x plus sine squared x over cos squared x.
Like that? Okay. I'm on board with that. We have a big fraction that we can split into two smaller fractions with the same denominator. What would this expression then simplify to? Rachel?
1 plus sine squared x over cosine squared x.
Yeah, here I think we could cancel out a cosine squared in the top and bottom to give us a 1. And what, I'm sorry, what did you say your second one was?
Plus sine squared x over cosine squared x.
Yeah, we could write it as sine squared over cosine squared. Is there another way we could write this sine squared over cosine squared? Mackenzie? Okay, Mackenzie?
Could it be tangent squared?
Hannah, what do you think?
I was gonna say use the Pythagorean identity.
Ooh, Pythagorean identity? Yeah, we could certainly use some of the Pythagorean identities stuff from the back of the sheet. Yeah, one way we could write this as sine squared over cosine squared is the same as just being tangent squared, since tangent is a single sine over cosine. So if we have 2 factors of sine in the top and 2 factors of cosine in the denominator, we can simplify to get 1 plus tangent squared. Another way we could have simplified, maybe I was curious which way you were going to choose. Does anybody remember, we said yesterday that cosine squared plus sine squared always is going to evaluate to the same thing. Yeah?
1.
Yeah, we said cosine squared plus sine squared always has to give us 1, mainly because cosine and sine are always going to give us the x and y coordinates of points on the unit circle, x squared plus y squared equals 1. So we could have said, at this point, just written this as 1 divided by cosine squared x, which even though we haven't talked about the secant function yet, we could it's going to turn out to be the same as secant squared of x. So either of these would be acceptable answers. But Dr. Gerstle, how can one function have 2 different derivatives? In general, a function should not have more than 1 derivative. It should just have a single one. But in this case, it checks out because these are always equal to each other. And this is actually one way that you could show secant squared and 1 plus tangent squared will always give you the same outcomes. So yeah, so for this function, tangent of x, once we know how to take the derivatives of sine and cosine, we don't have to use the limit definition again. We can use some of our derivative rules we've already found, which is quotient rule in this case, as Josh suggested. Any questions or comments? Speaking of secant x, let's take a look at that one. So the secant function, which is 1 divided by cosine, is similarly to tangent, not going to be as pretty as the original sine and cosine functions. Instead, it's going to look something a little bit like this. Let's see if this is positive 1. This is negative 1. It's going to keep looking like almost like a bunch of different parabolas. Like you got one here, jump up here, jump back down here, jump up here. Function's making all sorts of crazy jumps. And I think we can say similarly to tangent, this function is going to fail to be continuous at any odd multiple of pi over 2. Because just like how tangent was undefined at, say, pi over 2, Secant of x is also going to be undefined at pi over 2 because we get 1 divided by cosine of pi over 2 is 0. Don't divide by 0. That's your public service announcement for the day. So how can we differentiate secant of x? If nobody answers me, my default answer is going to be you use the limit definitions. Please somebody stop me. When?
We know how to differentiate cosine of x, so we can use secant's identity as 1 over cosine x to evaluate the derivative of 1 over cosine of x.
Ooh, okay. So similarly to how we used our knowledge of the derivatives of sine and cosine to differentiate tangent, we can kind of use some of our more general derivative rules along with those again to help us differentiate secant as 1 over cosine. I'm on board. So, how do you propose we can go about doing that, differentiating 1 divided by cosine of x?
Well, I would probably use the quotient rule. I don't think I'd rewrite it as cosine to the -1.
Oh, but that's the way I wanted to do it.
We can do that.
So we could do this the same way. Oh, my voice cracked there. We could do this the same way that we differentiated tangent of x to low, d high. Derivative of 1 is just 0. Minus high, d low. Derivative of cosine still negative sine. Let's go down below. But instead, I'm going to try using a different derivative taking rule, just for a little bit of review's sake. And we're going to write this as the derivative with respect to x of cosine of x raised to the -1 power. And instead of using the quotient rule, I think we can use the chain rule to help us differentiate this one. So if we wanted to use the chain rule to help us differentiate cosine of x and that raised to the negative power, I think our outside function is going to be taking thing to the -1 power, and our inside function is going to be cosine. So what would we get if we differentiated this using the chain rule? Huh?
So you'd take the derivative of the outside function, so and then have the inside function within, so be -1 times parentheses cosine of x to the -2. And then you'd multiply that by the derivative of cosine x, so negative sine x.
Like that? What do y'all think? Does it check out, or do I need to get the bucket? I love having just a bucket of water. It's just this amorphous thread at the front of the room. I should try to bring my own bucket of water to class. Yeah, I like it. So here, this would be our sort of g prime of h of x term, where we differentiate the outside. Derivative of thing to the -1 power is negative of thing to the -2 power by the power rule. And then the negative sine of x is sort of our h prime of x, the derivative of the inside function, which, as we saw last class, derivative of cosine is negative sine. This looks a bit messy. So first thing I want to do we got two negative signs, so I'm going to cancel those out because negative times a negative thing will give a positive thing. Also, I'm going to rewrite this in a sneaky way and say right now we have 1 over cosine squared times the factor of sine of x. I'm going to rewrite this slightly to give us sine of x divided by cosine of x multiplied by a 1 over cosine of x, which I think both of these should come out to the same thing of sine of x over cosine squared of x. So I think this is okay. We can pull the factor of sine of x outside and leave it by itself, or we can have a factor of 1 over cosine of x by itself. And what would be another way that we could write sine of x divided by cosine of x times 1 over cosine of x? Yes, Anna?
Sine over x over cosine of x is equal to tangent of x. And 1 over cosine of x is equal to secant of x.
I like it. Also, sorry, I'll stop doing that. So this is how I like to write this one out. That the derivative of secant x is tangent of x times secant of x. Ursula, I learned it was secant of x times tangent of x. Yeah, fine, write it that way if you like. For the record, if we had said secant of x, not lambda. For the record, if we had used the quotient rule to help us differentiate 1 over cosine of x, I think we would have come out to the same result in the end. We would have had to do some similar sort of algebraic manipulation of what we got, but it eventually would have simplified down to tangent of x times secant of x. Any questions or comments? Okay, that's all I want to do for now with regards to trig functions. Now, I want to talk about our next important topic, which is genies. What?
Genes or genies?
Genies. You know, rub a magic lamp, a genie comes out, grants you wishes. So, you're out in the desert one day. You find a magic lamp. A genie comes out. Genie gives you one wish. What do you wish for? As a poor college student, you wish for cash. You want money. Genie says, I will give you money in one of two options, but you get to choose which one. First option, I give you $10,000 right now in cash. So option one is Genie vanishes into a puff of $10,000 check or whatever. I don't know. Doesn't matter what form the money takes. But option one is $10,000. Option two, on the other hand, is the genie is going to haunt you for the next month, and he's going to give you start for 1 month. He's going to give you $1 today, but then tomorrow he'll show up and give you $2. And then the next day, he'll show up and give you $4. And then the next day, he'll show up and give you $8. And then this process is going to repeat for 1 month. Which option do you take?
Two,
Two?
for sure.
Why?
It's exponential. It'll be huge by the time you're done.
Oh yeah? For 1 month?
Mm-hmm.
How many days are we going to assume this month has?
31.
It's October. It's 31 days, Halloween. So we're going to assume this is a 31-day month. If you're doing this in February, by the way, you would get screwed. And the non-leap year. If you were to take option 2, it starts off very slow. You only get $1 today. It's not very much. $2 tomorrow. $4 the next day. $8 fourth day of the month. By the end of the month, where's my notes? At the end of the month, your grand total for how much money you will have made, just starting off with $1 today, $2 tomorrow, $4, these very small amounts. But if you keep doubling that amount each day, by the end of the month, your total that you will have earned is $4,294,967,295.
Told you, Joe.
That you have chosen wisely.
What if he kills you at the end of the month?
Hey, at least got a lot of money.
That was never part of the deal. You wished for money, not, I would like money followed by a swift death. I mean, if you wish for that, then sure, maybe you don't. Maybe you get a lot of money, but then you have to leave it to your.
Hey, my family's set for generations.
Yeah, I was gonna say, how much is that worth to you personally? Making the hard choices in calculus.
Generations.
So the moral of the story is that exponential functions start off growing slowly. You only start with $1, then $2, then $4. But by the end of the month, oh baby, that last day you made at the last day the genie gave you $2 billion and change. Exponential functions start growing very slowly, but then they will grow very, very, very quickly as time goes on. So, exponential function, on the next page of the packet now, if you want to follow along. Is function of the form f of x equals a to the x for some constant a, where a has to be greater than 0 and a is not allowed to be 1. Behold, arguably the most misused word in common speech from math. This word right here. Exponential. If someone in the news were to say, oh, this disease or this stock price or this whatever is growing exponentially, what do they usually mean?
They just mean it's growing by a lot every day.
Yeah, usually if someone says it's growing exponentially, they say it's growing by a lot, it's growing fast. Well, eventually that's usually the case. But if we start off, let's look at an example here. We'll look at f of x equals, let's say 2 to the x. That's not actually going to necessarily be the case. Because as we've seen, with say the genie example, by the way, this is what behaves just like the function 2 to the x. So this is 2 to the 0, 2 to the first, 2 squared, etc. And no, I did not actually add all 31 values together. I used a sneaky shortcut, which told me that the amount of dollars we have in total by the end of the month is 2 to the 32 power minus 1. But if we take actually no, you know what? I want more space. If we take a look at our exponential growth for say 2 to the x, ends up looking a little something like this. So if we were to plug in x equals 0, what would f of 0 be equal to? Rachel?
1.
2 to the 0 is 1, just like any non-zero number to the 0th power will give us 1. Boom. How about f of 1? 2 to the first power, going to give us a 2. How about f of 2?
4.
It's going to give us 1, 2, 3, 4. And then it's just going to keep growing from there. F of 3 is going to be 8, but I don't have enough space on my board to draw that out, so I'm just going to draw an arrow going up like that. What f of negative 1? What's that?
1/2.
Yeah, 2 to the negative 1, which will give us just a 2 in the denominator for a value of 1/2. That's negative 2. We'll get 1 over 2 squared, which is going to come out to a 4th. F of negative 3 is going to give us 1 over 2 cubed, which is 1/8, and so on. And so we end up with a function. It's going to look like this. It's a function that to the right, on the right half of the function, to the right of x equals 0, is yes, going to be growing very, very quickly. But if we look at the left side of our function, at values of x that are negative, it's not growing very fast out here. In fact, the further out to the left you go on your graph, your exponential function is going to be growing super, super slowly. So I would say exponential growth is fast for positive x and slow for negative x. That's why I say the word exponential often gets misused in the news. Everybody thinks exponential just means fast. It can mean fast, but it depends on what values of x that you're looking at. This looks like a continuous function. Are there any values of x at which this function does not exist, or at which the limit doesn't exist, or the limit and the function are different? Hannah? Yes, actual Hannah.
No.
Doesn't look like it. And so I would say that this function can be continuous everywhere. And in fact, it'll also be differentiable everywhere, as we'll see. Oh my gosh. Dr. Butterfingers up here. Let's take a look at another exponential function. Specifically, let's say g of x equals 1/3 raised to the x power. At x equals 0, we're still going to get a y value here of 1, because anything to the 0th power other than 0 is going to give us 1. G of 1 this time is going to give us 1/3, so a point like here-ish. G of 2 is going to give us 1/3 squared, which is a 9th. It's going to give us a point very close to 0. And in fact, the function is going to continue downwards in this way. What would g of negative 1 be? If we were to take 1/3 to the negative 1 power. Yeah?
3.
Yeah, the negative 1 power means we take the reciprocal of 1/3, which is going to become 3/1, which is 3. about g of negative 2? Avery?
9.
We're going to get, what, 3 squared over 1 squared, which comes out to 9, which is already too big for me to draw up here. I'm just going to draw it going like this. And g of x actually has a bit of a different shape than f of x. For something like a third to the x, as x gets bigger, g of x is going to be decreasing. The function that goes down as we move from left to right. So in general, anytime you look at an exponential function, it's always going to have one of these two basic shapes to it. For f of x equals a to the x. This is what happens if you look at a graph of f of x equals a to the x if a is greater than 1. So here our base a is 2. If your base a is something less than 1, then you're going to get a decreasing sort of graph like this. And so any exponential function is going to have one of these two basic shapes. Either something that starts growing really, really slowly, but then eventually picks up speed and starts growing really fast, or something that starts decreasing really, really fast, but then as x gets bigger, is going to start decreasing slower and slower as time goes on. Question. Why can't a be equal to 1? If we wanted to look at a graph of something like f of x equals 1 to the x, what would that look like? Well,
It'd just be a horizontal line and like 1.
yeah, 1 to any power is always just going to be 1. This function ain't so this isn't going to give us an exponential function. This is going to give us a linear function. It's going to give us a flat, constant function, y equals 1. That's why we don't generally want to include it when we're talking about exponential functions, because it doesn't have this sort of growth or decay like a to the x does for values of a other than 1. And the reason why we want a greater than 0 is because if we wanted something like f of x equals negative 2 to the x, it would be something like, it would be pretty crazy, constantly having to go between negative and positive values. Because negative 2 to any odd power, like negative 2 to the first, negative 2 cubed, negative 2 to the fifth, is always going to give us something negative, because we have an odd number of negative signs, which cancel out to give us a single negative sign. Whereas if we were to take something like negative 2 squared, negative 2 to the fourth, negative 2 to the sixth, plugging in even numbers for x, all of a sudden we would be getting positive numbers because we'd have an even number of negative signs when we multiplied that out. And we'd get stuff like negative 2 squared is positive 4. Negative 2 to the fourth is positive 16. And we'd be getting positive outputs. So for a graph that sort of behaves like this, something that's got this nice smooth curve to it, we need that a can't be 1, because a equals 1 is too boring, just a flat line. And we need that a has to be positive, because a being negative would be not boring enough. Too much happening there with that function. Any questions or comments about exponential growth? So, now that we've talked about exponential functions, let's go to their big, scarier brother, talk a little bit about logarithms before we start talking about how we differentiate these. So logarithms are a bit less intuitive, but they're very much related to the idea of an exponential function. And we'll talk about more specifically how that is. Where's my chalk? And a logarithmic function is going to be a function that has form f of x equals log base a of x for some a greater than 0 and a not equal to 1. And the reasons why a has to be positive and not 1 are going to be similar as they are for the exponential function, where log base a of x is going to be b is the same as saying that a to the b power is going to give us x. So whatever your output b is to the log base a of x, whatever that b is should be some number that if you were to take a to the b power would give you back x. So let's take a look at this. See what would a graph of one of these log functions look like. Let's do a equals 4. So we'll do a log base 4 of x. And these are a little bit trickier to kind of evaluate values for, because you're not just plugging values of x into exponents. So if we want to say that log base, let's say we wanted to find log base 4 of x equals 1 to start. According to the definition of logarithm, we're looking for a number, which we're going to put in this blank, that'll make it so that 4 to whatever this blank power is should be equal to 1. So what exponent do we need to raise 4 to the power of in order to get 1?
Would that just be 0?
I think so. 4 to the 0 powers should be 1. In fact, anything to the 0th power should give us 1. So what that tells us is since 4 to the 0 is equal to 1, f of 1, which is log base 4 of 1, should be equal to 0. So on our graph of the logarithm, if we go to x equals 1, we're going to get a y value here of 0. Let's skip all the way to log base 4 of 4. What power would we need to take 4 to in order to get back just plain old 4? When? 1. Yeah, 4 to the first power gives us 4, because we have one factor of 4, that's a 4. So that's going to tell us that log base 4 of 4 should also, or f of 4, should also be equal to 1. How about log base 4 of 2? In other words, what power do we have to take 4 to in order to make it so that 4 to some power will give us 2? Avery?
4 to the 1/2.
4 to the 1/2. In other words, square root of 4 should give us 2. So I think that f of 2, or log base 4 of 2, should be equal to half. Let's do a couple more. Let's look at, I don't know, f of a 4th. What power would we have to raise 4 to in order to get a 4th? Hannah? -1, I like it. Because taking something to the -1 power just means taking its reciprocal, as we've seen. So that tells us that at x equals a 4th, we should get a y value on this graph of -1. So we'll get a point like this. And finally, let's look at f of 0. Tempted to ask Dr. Volasov as she passes. Four to what power is going to give us 0? I see you shaking your head over there. What does that mean?
It means nothing.
Nothing? We can't take 4 to any power and get 0? Dad Zeus. Yeah, 4 to a positive power will always give us something positive. 4 to a negative power will also still give us something positive. 4 to the 0 is going to give us 1, which is positive. F of 0 does not exist. There is no number we can take 4 to the power of in order to get 0. And so f log base 4 of 0 is undefined. So if we were to sort of connect our dots and make a graph, sorry, you guys, I need to make some space. We're going to get a graph that ends up looking something a little bit like this. What's different about the shape of this graph and the shape of, say, 4 to the x, where this was f of x equals log base 4 of x, and if we were to graph out, say, g of x equals 4 to the x, it's going to look something instead like this. What's different about these two graphs? Well,
They seem to be mirror images.
yeah, if you take your head, tilt it 45 degrees, they seem to be mirror images of each other across this line right here. That's interesting. Have a good day, everybody. See you all on Friday. So on Friday, we'll investigate this mystery some more, talk about the relationship between exponential and log functions, and then we'll also start looking at how do we differentiate these sorts of things. Oh, but I love it. Good job today. Nobody had to get bucketed.